Formal definition of a matrix. Hello everyone. In our previous conceptual introduction, we observed how data from a table can be simplified by removing descriptive labels to focus purely on the numerical values. Now, we will transition from that intuitive understanding to a formal mathematical definition. Let us begin with the primary question: what is a matrix? Formally, a matrix is defined as an ordered rectangular array of numbers or functions. To ensure we fully grasp this definition, let us break down the key terms used here. First, the term ordered. This means that the position of each number within the array is fixed. This is a critical point. If you change the position of even one number, you have changed the matrix itself. Next, we have rectangular array. This refers to the arrangement of elements in a grid-like structure. This grid consists of horizontal lines, which we call rows, and vertical lines, which we call columns. It is described as rectangular simply because the overall shape of this arrangement resembles a rectangle. Finally, let us look at numbers or functions. While we most commonly deal with real numbers in high school mathematics, it is important to note that the entries within a matrix can also be algebraic expressions or mathematical functions. Now that we have established this formal definition, we will move forward to discuss the individual components that make up these arrays. Elements of a matrix. Now that we have established the formal definition of a matrix as an ordered rectangular array, let us look closer at the components that make up this structure. The individual numbers or functions that are arranged within a matrix are formally called its elements or entries. You can think of these as the basic building blocks of the matrix. To be more precise, if we consider a matrix A, an element is a single value located at the specific intersection of a row and a column. This fixed position is what makes the array ordered, as we discussed in the previous slide. For example, if we have a matrix containing the numbers 1, 2, 3, and 4, each of these individual numbers is an element of that matrix. In the next slide, we will discuss the specific mathematical notations used to name these matrices and their elements to ensure clarity and consistency. Mathematical notation. Now that we have a clear understanding of what a matrix is and what we call its individual components, let us discuss how we actually write them down. To maintain consistency and clarity in mathematical communication, we use specific notations so that mathematicians everywhere are speaking the same language. First, let's look at how we name a matrix. A matrix is always denoted by a capital letter. For example, you will typically see them labeled as capital A, capital B, capital C, capital X, or capital Y. Using a capital letter allows us to easily distinguish the entire matrix structure from the individual elements within it. Next, we need to consider how to enclose the elements. To indicate that a set of numbers forms a rectangular array, we wrap them in either square brackets or parentheses. While both are mathematically acceptable, if you are following the NCERT curriculum, you will find that square brackets are most commonly used. Keep these notation rules in mind, as we will apply them in the next slide when we transform a real-world data table into a formal mathematical matrix. Real-world example: formalizing data. Now that we have established the formal definition, the concept of elements, and the standard notation, let us see how we move from a real-world scenario to a formal mathematical matrix. Imagine a scenario where a teacher wants to record the marks of 3 students, Amit, Beena, and Chitra, in 2 subjects, mathematics and physics. Step 1 is to organize this data in a traditional table. In this table, the first column lists the students, the second column shows their marks in mathematics, and the third column shows their marks in physics. For example, Amit has 85 in mathematics and 78 in physics, Beena has 92 and 88, and Chitra has 79 and 84. In step 2, we transition toward a matrix by removing the descriptive labels. We strip away the names of the students and the names of the subjects, keeping only the numerical data. It is vital that we keep these numbers in their exact same relative positions, as we discussed earlier that a matrix must be an ordered array. This leaves us with 3 rows of numbers, 85 and 78 in the first row, 92 and 88 in the second, and 79 and 84 in the third. Moving to step 3, we apply the notation we learned in the previous slide. We enclose this rectangular array of numbers within square brackets to give it a formal mathematical structure. Finally, in step 4, we assign a capital letter to denote the matrix. Let us use the capital letter M to represent this Marx matrix. We would write this as capital M equals the matrix containing 85 and 78 in the first row, 92 and 88 in the second, and 79 and 84 in the third. In this formal representation, the entire structure denoted by capital M is the matrix, and the individual numbers, such as 85, 78, and 92, are the elements of the matrix. This practical example bridges the gap between raw data and mathematical notation, which we will summarize in our key takeaways in the next slide. Key takeaways. First, let's revisit the core definition. A matrix is an ordered rectangular array of numbers or functions. Remember, the term ordered is crucial here because the specific position of each value is what defines the matrix. Secondly, as we discussed when looking at the individual values, the components that make up the matrix are formally called elements or entries. In terms of notation, always remember that we denote the matrix as a whole using capital letters, such as capital A, capital B, or capital C. This helps us distinguish the entire structure from the individual values inside it. Finally, to keep the array organized, the elements are always enclosed within either square brackets or parentheses. Now that we have seen how to transition from a real-world data table to a formal mathematical structure, let us summarize the key takeaways from this lesson to ensure we have a solid foundation. With these fundamental rules in mind, it is very important that we discuss how to apply them correctly. Let us move to the final slide to examine some common mistakes you should avoid to ensure your notation remains precise. Common mistakes to avoid. First, be careful not to confuse the matrix itself with its individual elements. It is a common error to use the same notation for both. To keep them distinct, remember that the matrix refers to the entire structure, the whole container, and is therefore denoted by a capital letter, such as capital A. On the other hand, the elements are the individual values located inside that structure, and these are typically denoted by lowercase letters, such as lowercase a. Secondly, you must not ignore the order of the elements. As we established in our very first slide, a matrix is specifically an ordered rectangular array. This means that the position of every single entry is fixed and significant. If you were to swap the positions of even 2 elements, you would not be looking at the same matrix anymore. You would have created a completely different matrix. Finally, please be mindful of your notation. A frequent mistake is using lowercase letters to name the matrix itself. To maintain consistency with mathematical standards, always use capital letters when naming a matrix. For example, you should use capital A, not lowercase a, to represent the matrix. Now that we have covered the formal definitions and seen a practical example, let us discuss some common pitfalls to avoid to ensure your mathematical work is precise.